All right, guys, we're here in our last lesson. We're looking at collisions in two dimensions. So basically, collisions at an angle. So we're dealing with any type of collisions in two dimensions. The main thing we have to remember is that momentum is a vector, which means it's going to have magnitude and direction. So this is kind of helpful because when we're trying to find the total momentum, we have to remember that momentum is conserved. We also have to do some vector addition. All right. So, little example here. We're going to start by looking at collisions at 90-degree angles. So when two objects are colliding and the angle between them is 90 degrees. Right? These are going to be a little bit simple. So we have a 750 kilogram Pugo, which is a pretty small car, traveling at 21 meters per second west. It collides with a 680 kilogram Fiat, which is an even smaller car, traveling 18 meters per second south. The two cars become entwined. What is their total final velocity as they are traveling together? All right. So again, any of these problems, kind of helpful to kind of look at them visually first. Right. So we have our first car. All right, we got the Pugo. Right. And it's traveling west. Let's establish a couple things about it. We know that its mass is 750 kilograms. Its initial velocity is, we'll say, 21 meters per second. All right. We can figure out its momentum, which is just going to be mass 1 times velocity 1. That's going to be roughly 15,730 kilograms meters per second. All right. So just very quickly, we're able to figure out what the momentum of the first car is, the Pico. Now, we can then figure out the momentum, velocity, all that of their second car, our little Fiat. Right. So we have this traveling downwards, or traveling south rather. A few things we know about it. All right, its mass is 680. Its velocity is, what was it, 18. And its momentum, if we add those two together, multiply them together, we get roughly 12,240 kilograms meters per second. All right. So, know two things already. And we want to look at, okay, what's happening during this collision. So let's simplify this a little bit. All right. So we have, let me be consistent with my colors. All right. So we have the motion of our Pugo. And we also have the motion of our Fiat. Right. Now notice, right, makes a 90-degree angle. And we know when you're going to get a 90-degree angle like this in a collision, right, we can know instinctively that the result is that they're going to move roughly at a diagonal angle. All right. And this is going to be what we can consider the total momentum. All right. And that's going to equal our total initial momentum, which is also going to equal our total final momentum. Now, crucially, one thing that's important here, so we know that in a collision like this, right, we're going to have an angle here. We don't know necessarily what that is yet. But what's helpful here is since we have a simple right triangle and we already know two sides, right, we know what this momentum is and what this momentum is, we can just use Pythagoras to figure out this third side. Okay? So we end up with our total momentum is going to be equal to square root of our initial momentum here squared plus our initial momentum here squared. All right. And then plug in all our numbers, do the math. We're going to get roughly 20,000 kilograms meters per second. Right? It's just under, so about 19,947 kilograms meters per second. All right. A couple other things we can do here. We can still solve for what this missing angle is, right? Because this is going to tell us, when we're talking about momentum, it's helpful to know which direction it's moving in. In order to know which direction our vehicle is now moving in, we need to figure out our angle, theta. Now, in this case, because we know two sides, neither of them are the hypotenuse, we can use our inverse tangent function. So I do, let's see, do opposite over adjacent, so pi. Plug in our numbers here. Let's go and plug in my calculator. And I get roughly 52 degrees, and this more specifically is going to be 52 degrees west of south, right? But we're not done yet, right? Because what the question is really asking is, it's asking what is the total final velocity, right? What is VF? Now, we've kind of done the hard work here, right? Because we found our total momentum, right? It's just under 20,000 kilograms meters per second. Now, our total momentum is going to be given, considering that the two cars are now entwined as one. So our mass is going to be the total mass of the two cars, right, times the final velocity, right, because they're moving with the same velocity since they're intertwined. Since we're solving for final velocity, we can isolate that. So we get final velocity equals total momentum divided by total mass. Plug in our numbers, right? It's about 20,000 divided by, what was it, 13? Okay, yep. Plug in our numbers, so total mass, 750 kilograms plus 680 kilograms. Get that divided. We're going to get roughly 14 meters per second, and it's going to be 52 degrees west of south. There's my answer. All right, so again, a couple things I had to do here is draw it out, right? I realize that a 90-degree collision is going to also create a right triangle. And that right triangle is going to give me, or the hypotenuse is going to be the total momentum. Right? I can solve the total momentum by using Pythagoras. Can use the inverse tangent function to figure out the direction that it's going to move in. And then from there, everything else is just plugging in, what am I needing to find. Okay. So, key thing is, we need to remember that momentum is what is conserved, right? The law of conservation of momentum is that momentum is conserved. So the total momentum before collision is going to be equal to the total momentum after collision. So in order to figure out what that is, right, we need to add the momenta, right? Not adding velocities. All right. So 90-degree collision, relatively simple, relatively straightforward. Again, just ends up being some plug and chug math. But because we can't have nice things, we're also going to look at collisions that are not at 90 degrees. Right? This is obviously more real world. So in this case, we have a 4-kilogram bowling ball moving with an unknown velocity. Right, so got our bowling ball moving, initial velocity. We don't know it. We don't know its mass though. 4 kilograms. All right, and then it is going to collide with a frozen cantaloupe, as you do. Very common real world scenario. We could say we know that's at rest, so its initial velocity is 0, and its mass is 6.1 kilograms. All right. So after the collision, we see, kind of like in pool or billiards, right? If you hit the cue ball, the white ball, and it hits a ball kind of at an angle, right? Not perfectly straight on. You already know that those two balls are going to bounce kind of in opposite directions. Okay. So what we have is we have our bowling ball is going to be moving at an angle. Right. And that velocity is going to move with is going to be 2.8 meters per second. Right. Now, a key thing here is we know that this bowling ball is going to be moving 32 degrees north of east. Our cantaloupe, on the other hand, was rudely knocked out of place and is moving kind of in the opposite direction, right? So it is moving 41 degrees south of east. And it has a final velocity of 1.5 meters. Now, we know the result. Our goal here is to try and find, okay, well, if this is the case, what was the initial velocity of the bowling ball before this collision? Now, in a problem like this, there are multiple ways to go about it. We're going to go with probably the simpler way first, right? The way where we're going to be able to break this down just using some pretty simple math. Hard to make a mistake besides just simple errors, right? And basically what that means is we're going to take each of these new velocities and we're going to break them down into their x and y components. So we're going to start with our bowling ball. Right. Just want to be consistent with my colors. Okay, so we're going to start with our bowling ball. Right. So in this case, right, we have our momentum is going to be equal to the mass times the final velocity. We plug our mass of the bowling ball, 4 times the velocity, 2.8. We're going to get a momentum of 11.2 kilograms meters per second. Okay, so that's the momentum that it's moving with in that direction. However, what we want to do here is we do want to break this down into its x and y components. Okay. So we can say we got P1y and P1x. And we have our angle here, which is 32. Now, this is pretty simple. Again, this is what we've been doing all year, right? We're just breaking down a two-dimensional motion into its x and y components, right? So we see if we want to know the y direction, right? This is the opposite side. We're just going to use sine. So we have our hypotenuse, which we already found. It's 11.2 sine 32, which equals 5.935 kilograms meters per second. Okay. The x direction, right? This is the adjacent side, so we're going to use the cosine. So 11.2 cosine 32 will be equal to 9.498 kilograms meters per second. Right. Now we do the same thing for our blue ball. Right. Again, this is a good time to kind of pause, do it yourself before kind of watching the solution. So same thing. Just kind of drawing out my diagram. Right, I know that my final momentum of this ball is going to be given by my mass times the new velocity. So the mass of my cantaloupe is 6.1 times the new velocity is 1.5. So the final momentum here is going to be 9.15. Right, gives me my hypotenuse. But what I'm looking for, I'm looking for my momentum in the x direction and my momentum in the y direction. Right. So just like what I did, if I want to know the x direction, right, this is my adjacent side. So I get 9.15 cosine 41 equals 6.906 kilograms meters per second. The y direction, right, it's going to be my sine. .003. So relatively straightforward. Move on to the next page. All right, what I want to do here is to find our total momentum. I want to add up my momentums in the x direction together and my momentums in the y directions together. All right. So looking at my two momentums in the x direction. All right. So pulling from up here, I have 9.498 plus 6.906 equals 16.4 kilograms meters per second. Right? So that's my momentum in the x direction, total momentum for both balls. Right? Now I can do the same thing for the y. Right? My momentum in the y direction of the bowling ball is 5.935 plus momentum of the cantaloupe in the y direction. One thing I should have mentioned, all right. So both balls are moving to the right. So, right, those are in the positive direction. The bowling ball is also moving up, which is positive, and the cantaloupe is moving down, right? So actually, key thing here, right, this down direction is going to be negative. So moving to right, positive, moving up, positive, moving down, negative. So actually what we end up here is we end up with negative 6.003, which brings us to a number, right, 0.068 kilograms meters per second. Now, you might look at that number and think, wow, that's a really small number for two relatively heavy balls moving with not insignificant velocity. So here's the key thing though, right? It is correct that we would find a small number, and more accurately, what this number should be is it should be about 0. Right? You might be wondering why, right? Both the bowling ball and the cantaloupe are moving, up and down. The key thing here, though, is that the momentums in the y direction really should cancel out, because initially, as the bowling ball is moving, right, it is only moving in the x direction, right? The y momentum initially is 0. And so while we do have a y momentum after the collision, the y momentum of the bowling ball is canceled out, or should be canceled out, by the cantaloupe. So again, all our total momentum is in the x direction. The only reason why we didn't get 0 is just through some, just like rounding errors and, sig figs, etc. Right. Now, once again, we're not done. Right. If we go back to the initial problem, right, we're looking for what was the initial velocity of the bowling ball. We haven't found that yet. All we found is kind of our total momentums. So we know that our initial velocity is going to be equal to our velocity in the x direction. It's going to be equal, in this case, to our final velocity in the x direction, which we found to be 16.4 kilograms meters per second. Right. Now, once again, I know my velocity, or sorry, my momentum formula is momentum, mass times velocity. I'm trying to solve for velocity, so I get velocity equals momentum over mass. Found my momentum total, divided by my mass. I get an initial velocity for my bowling ball, 4.1 meters per second east. All right. Again, this was a little bit simpler to solve for because my cantaloupe initially was at rest, meaning it had no momentum, so all the momentum in the system was held by the bowling ball. So it made it a little bit easier to solve. All right. Next, we have another method that we can use to solve for this problem, or problems like it. Now, this one is a little bit faster because we can do it essentially all in one diagram, but a little bit simpler to make some mistakes, right? It just kind of depends on, I would say, your proficiency in just basic geometry. So if we use the vector addition method, right, simply what we can do is add the vectors and solve with the sine or cosine law. So you'll notice that the total momentum is either initial or final because our momentum is conserved, right? The initial momentum should equal the final momentum. Okay. So, a couple things here. So we started with our momentum of the bowling ball after the collision, right? And we already found this. Our momentum of the bowling ball after collision, in order to find that, right, it's just taking the mass of the bowling ball times its velocity. Right? We've got 11.2 kilograms meters per second. And we know that this collision happened, or the direction it was moving, was 32 degrees above east. We also had the collision and resulting velocity of the cantaloupe. And we found that this momentum, when we took the mass of the cantaloupe and multiplied by the velocity it now had after the collision, which was 1.5, right, we got 9.15 kilograms meters per second. Now, we know that this velocity, or this motion, was 41 degrees south of east. Using our geometry angle rules, forgot the exact name of this rule, right? We know if this one 41 degrees, this is going to also be 41 degrees. Right. And then, because we know that all triangles, all three angles are going to add up to 180, we know that this missing angle here is just going to be 107. Okay. So down here, this is going to give us our total momentum, which is equal to our final momentum, which is equal to our initial momentum. Now, when we're solving for this, again, you can use the cosine law, sine law, kind of whichever you are the most proficient in or most comfortable with, right? So when I'm solving for all these sides, right, I'm just going to use the sine law. I think it's a little bit easier. All right, I'm going to take my total momentum divided by the sine of 107. And I know that's going to equal my side 1 over sine 41. I know in this case, if I'm trying to find the total momentum, I'm going to isolate for that. To end up with my first side, sine 107 over sine 41. It's going to equal 16.33 kilograms meters per second. Now, once again, still trying to solve for that final velocity. I'm going to take that same formula that I isolated before, right? Velocity equals momentum divided by mass. Right. Taking my total momentum I found, divided by the mass of the bowling ball. Do a little bit of rounding. End up with 4.1 meters per second east. Done. All right. So a lot faster than our previous method, right, where we broke down all of these motions into X and Y components, added them all. Okay, use that to find our answer. Again, the only difference in some of these answers, well, we got 16.4 and 16.33, right? We're just getting some rounding errors or differences. But a lot simpler. I would say not a lot simpler, a lot faster. But again, this is more if you are feeling pretty comfortable with your geometry skills, that you can pull those out of the bag. But two different methods to solve the same problem.